Hello everyone and welcome back. Today I'll be talking about thermochemistry and the mechanism of acid-base reactions. I'm also gonna be talking about reactions between molecular structure and the acidity. Before we start this part, we need to know what do we mean by reaction mechanism. Reaction mechanism describes in details how reaction occurs. It describes to us which bonds are gonna be broken and which bonds are formed. In the concept of thermochemistry or the study of thermochemistry is the study of the energy of the entire system at every instant of the reaction. We all know that for any chemical reaction to happen, the reactant have to be moving with a certain speed. If they are moving so slowly, no reaction will happen and the molecules bouncing to each other will not be able to break their bonds and reform it again. While if they are not facing the right direction, the molecules is not facing the right direction of the bond, the other molecules, also molecules would bounce back without any direction. For any reaction to happen, the reactants have to have energy. This energy have to be enough to break down the bond between the reactant and reforming them in the products. And also the orientation of the reactions of the reactant have to be in a certain direction that allow the atoms to meet and bind together again in order to form the product. In any chemical reaction, there is what we call a transition state. The transition state is a state where we will have partially broken and partially formed bonds. It's a strained state. This is why the transition to a new structure happens to a less strained one. We use the reaction coordinate diagram to show the flow of the energy or the energy changes during a chemical reaction. The vertical axis shows the energy and the reaction coordinate, the x-axis, horizontal axis is actually shows the progress of the reactant into the product, or the progress of my reaction. It doesn't indicate, it is not a time plot, so it is not against time. In here you have two wells. These two wells means they are more stable component, so my reactant are stable once they are given a free energy of activation. This free energy of activation will activate my reactants to form what we call a transition state. This transition state, as you see here, is the highest peak of my curve. This means there is a high strain on that structure. This is why it loses energy and it forms a more stable compounds, which are my products. For reactants at a constant pressure, we indicate the energy of the reaction to be a Gibbs-free energy. The Gibbs-free energy with this node means we are at standard conditions equal to minus RT ln K equilibrium. The R is the gas constant, T in Kelvin, temperature in Kelvin, and ln K equilibrium. K equilibrium is the and K equilibrium is the equilibrium constant of my reaction. The Gibbs-free energy dedicate which the position of the equilibrium and also dedicates the rates of the chemical reaction. If my Gibbs-free energy is less than 0, this means the products are favored. While if I have a Gibbs-free energy bigger than 0, this means my reactant will be favored. Now let's look at this exercise. Calculate the Gibbs-free energy for a reaction with a K equilibrium of 1 multiplied by 10 to the power 3 at 298 Kelvin. So the Gibbs-free energy is equal to minus RT ln K equilibrium. This means minus R in that case is equal to 8.31 multiplied by my T is 298 multiplied by the ln of this number 1 multiplied by 10 to the power 3. This will give me minus 17,900, which joule per mole, which I can transfer it into kilojoule per mole if I divide it by 1000, so it is 17.1. Now moving to the Gibbs-free energy of activation. Gibbs-free energy of activation, which takes this sample, is a difference between the reactants and the transition state. It controls how fast the reaction or the rate of the reaction and the ability of the reactant to achieve the transition state. It is always positive and it is have a higher energy than that of the reactants. The difference between the Gibbs-free energy of my product minus my reactant can tell us if my reaction would be accompanied by energy or by releasing energy or absorbing energy. So if my reaction is exogenic reaction, this means it will be accompanied by releasing of energy, and in that case my Gibbs-free energy G for product will be lower than my Gibbs-free energy of my reactant. And the position of the equilibrium for the exogenic reaction would favor the products. In that case, the delta free energy would be negative value, will have a negative value. The endogenic reaction is a reaction in which the Gibbs-free energy product is higher than the reactant. So I have the Gibbs-free energy of the product is higher than the Gibbs-free energy of my reactant. In that case, the position of the equilibrium would be in the endogenic reaction would favor the starting material of the or the reactant, and the Gibbs-free energy would have a positive value. So the change in Gibbs-free energy is a function of a change. This is why, and it's actually a function of a change of two parameters, the enthalpy and entropy. So we could say that delta free energy, Gibbs-free energy, is actually equal to the delta of the enthalpy minus the temperature multiplied by the delta of the entropy. The enthalpy this value is the energy contained in the bond and the solvation energy. Now let's look at the relation between the Gibbs-free energy, enthalpy, and entropy. If I have an entropy less than 0, but I have enthalpy larger than 0, the Gibbs-free energy, like we said before, is equal to the change in the enthalpy minus temperature delta entropy. This means if I have this value less than 0 and I have large value of delta H, this means my delta G, Gibbs-free energy, is larger than 0, and in that case the position of the equilibrium would be favored in the direction of the reactants. Now what if I have the enthalpy less than 0? I still have my entropy less than 0 and I have my enthalpy less than 0. This means the total delta G Gibbs-free energy would be less than 0. And in that case, the position of the equilibrium would be favored in the direction of my products. The other case, so I assumed that the first I put the delta entropy less than 0. Now I will put my delta entropy larger than 0. And if I compare it, if I have larger entropy larger than 0 and I have large enthalpy, this means at a higher temperature, when the temperature multiplied by entropy larger than the enthalpy, my Gibbs-free energy would be less than 0. And the product would be more favored. If I have entropy larger than 0, but I have my enthalpy less than 0, this means the total, because the entropy would give me a minus value for the Gibbs-free energy, this means my delta G would be negative or less than 0, and the position of my equilibrium would be favored in the product. As a summary, you could see that in 3 cases, the relation between the Gibbs-free energy and the enthalpy and entropy would be favor the product unless I have enthalpy larger than 0. So this is the only case where if I have enthalpy larger than 0, my reaction would favor my equilibrium would be favored in the direction of the reactants. Now, if I looked at the mechanism and thermochemistry of acid-base reactions, the acid for base to accept a proton from an acid, the two entities, the acid and the base, like we said before, in any reaction they should collide. The direction of the base during the collision have to be toward the proton. So if the proton is not toward my base, the reaction will not happen. The proton is also partially shared between the acid and base. If we try to look at the steps or the mechanism of acid-base reaction, we could see that if I have an acid that's reacting with a base, and if you look here, I have these two non-pairs electrons, non-bonding electrons that will move to my acid, and this bond will move to the oxygen. A sharing of the hydrogen, which is the proton in that case, between the base and the acid. This is my transition state, the highest energy. Then I move from that one. This bond will break and this bond will reform. So I will have a conjugate base and a conjugate acid. The molecular structure can affect my acidity. One factor that can affect the acidity is one of the factors that can affect the acidity is the electronegativity of the atom pairing electron charge. If we look here at this first compound, ethanol, we have a nitrogen which is a higher electronegative. Methylamine, the nitrogen here has a lower electronegativity comparing to oxygen, and ethane actually doesn't. The electronegativity is very low comparing to methylamine and ethanol. If we look at the value of the pKa, we could see here is approximately 51. For methylamine is 38, and for methanol is 16. Like I said before, increasing the pKa value decrease the acidity. This is why the methanol have the higher acidity due to the presence of the high electronegative oxygen comparing to methylamine and ethane. So the other factors that affect my acidity is the size of the atoms bearing the negative charge. If I have something like methanothiol that reacting with the methanoxide to form methanothioate ion and the methanol, you could see that the pKa of my acid is equal to 10.4, and my pKa of my produced methanol acid is actually equal to 15.5. You have to remember, the larger the value, the weaker the acid will be. This means in that case, the methanol is less acidic than the methanothiol. The reason for that, if you compared the three-dimensional structure or the geometry of the methanothiolate ion comparing to the methanoxide ion, you could see that it is larger. So the methanothiolate is larger than the methanoxide ion. This means the distribution of the electrons will be more stabilized in that case. This will give me a more acidic character for my molecule. The other factors that can affect the acidity, the delocalization of the charge in the anion. This will give me if I looked at an alcohol and acetic acid, you could see that the acetic acid have this ability to form what we call resonating structure, while here, so the delocalization of the electron over the two oxygen would give me two resonating structure, while here in case of alcohols, they are not forming this resonating structure, only the alkoxide ion is formed. This is why the acidity of the acetic acid with two resonating structure is more acidic than the alkoxide. So this is why the alcohols have lower acidity than the acids. The factor that can affect my acidity is the inductive effect. and the electrostatic stabilization of the anion. We mean by the inductive effect the polarization of the electron density of the covalent bond caused by the electronegative nearby atoms. If you looked here at trifluoroethanol, we have substituted the hydrogens with fluorine atoms. This would create what we call inductive effect between the oxygen and the fluoride atoms. This inductive effect, the delocalization of the charge, will stabilize my structures. This is why the pKa of the trifluoroethanol is less than the pKa of the ethanol. This is what makes the trifluoroethanol more acidic than the ethanol. Yet you could see that if I increase the distance between the two electronegative atoms, I will decrease the effect of the inductive. I will decrease the inductive effect. If I have here the fluorine atom and the oxygen, they are near to each other. But if I increase the distance by inserting one methyl group, I could see that I'm decreasing the acidic character by increasing the pKa, and even if I add another carbon, I'm decreasing the acidity and increasing my pKa. This inductive effect will affect also the acidity of the halogen substituted carboxylic acid. You could see that chloroacetic acid would be high in acidity comparing to acetic acid due to the inductive effect between the chlorine atom and the oxygens, nearby oxygens. For the chlorobutyric acid, I have pKa of 2.83 that would increase the value. This means I'm decreasing the acidity in that direction, decreasing. This decreasing in the acidity due to the insertion of due to the moving of the chlorine further away from the two oxygens. So the distance, increasing the distance, will decrease my acidity due to the decrease in the inductive effect. The last factor that can affect my acidity is the hybridization and the presence of S character of the atom pairing negative charge. I mean that if I have alkalines and if I have alkenes, I could see that here I have triple bonds and in here I have double bond. This triple bonds and double bond will affect my acidity. The higher the higher the unsubstituted hydrocarbons will be, the higher acidity it will be. This means if I have triple bond, I have higher acidity, double bond, I have lower acidity, comparing to even just a sigma bond. This happens because my pi bond, like I said before, is actually electron donors. And these electron donors would increase the acidity. So you could see alkalines is actually have higher acidity than the alkenes, and the alkenes have higher acidity than the alkanes. In acid and bases, there are a few examples in which I don't have any protons in between. This is what we call them Lewis acids and base. In Lewis acid and base, a proton donor, which is my base, would donate electrons to the Lewis acid, which is acceptor, and a new covalent bond would form in what we call Lewis acid base reaction. In that case, my Lewis acid would be the proton acceptor, and it will acquire a negative formal charge and at the end of the reaction, while my Lewis base is the donating part for the pairs of the electrons, and it will acquire a positive charge. We could say that all pronounced Lowry acids are actually protic acids. Protic acid, we mean by protic, contains protons. But Lowry acids, they can be protic acids, they can contain protons, or they can be aprotic acids. They can form in absence of any protons. Like in here, diacyl ether is a Lewis base that donates its electron to boron trifluoride, and that case what will form a covalent bond between both of them, and the new boron trifluoride ether complex is actually the Lewis acid base component. Now, this is the term that we usually call this part, which is the Lewis acid. We name them electrophiles because they need the electron and they have a low density of electrons. So by electrophiles, we means by that loving electrons. They love to acquire electrons. The nucleophile, on the other hand, is the Lewis base. They don't have they seek the area which they have a lower electron density because they have they have a higher electron density. So this in Lewis acid is actually an electrophile, and the Lewis base is actually an nucleophile. Now moving to this last exercise. Write an equation for the reaction between each Lewis acid base pair showing electron flow by means of curved arrows. So my first reaction in that case, boron trifluoride. So I just have to draw the bonds plus NH3. In that case, I have here 2 lone pair, and this 2 lone pair would move to this boron. So I will form the covalent bond between the Lewis acid and the Lewis base, and the Lewis base will acquire a positive charge. My Lewis acid will acquire a negative charge, and I can just write down the last of the remaining of the bonds around my 2 atoms. Now for this one, you can see I have here positive charge and here I have negative charge. So if I try to draw them, and because I have here positive charge and the Cl, if I draw the negative charge, this means I have extra negative charge on my chlorine atom. So the covalent bond, or the bond between the Lewis acid and Lewis base, would form, and in that case, if I count the formal charge around my carbon right now, I could see that it is 4 electrons, so I don't have to write down the positive. And in here 1, 2, 3, 4, 5, 6, 7, I have 7 electrons around my chlorine atom, so I don't draw the negative charge. So I only draw when I acquire more positive or more negative charge. If you could count here in that case, for the formal charge around my nitrogen, 1, 2, 3, 4, so it is less than my actual charge. My actual charge on my nitrogen should be 5, so now it became 4, so I have to write down the positive. For my boron, in here, I have 1, 2, 3, 4, so it acquired extra negative charge above it because the boron only have 3 electrons around it. By that, we came to the end of our chapter 4. Thank you and goodbye.